Okay, so we've all seen the periodic table, right? But what if I told you it's not just some boring chart of elements? What if it's actually a treasure map? One with a secret code that predicts how every single element behaves. Well, in the next few minutes, we're going to crack that code together. Have you ever wondered why elements in the same column, like lithium, sodium, and potassium, act so much alike that scientists literally call them a family? Yeah, that's not some happy accident. There are real fundamental rules at play here, and we're about to pull back the curtain and see the why behind this amazing setup. So, here's how we're going to do this. We're going to build this thing from the ground up, one layer at a time. First, we'll tackle the most basic thing, the size of an atom. Then we'll see how that size changes its grip on its own electrons. And finally, we'll figure out how all that affects its power to attract electrons from other atoms. It all connects, you'll see.
All right, first up, let's talk about atomic size. Seriously, this one simple idea is the bedrock for everything else we're about to get into. So, how in the world do you measure something you can't even see? Well, we use something called the atomic radius. It's basically the distance from the very center of the atom, the nucleus, all the way out to its most distant electron. You can almost think of it like the atom's wingspan. So what actually decides how big an atom gets? Well, it's basically a constant tug of war happening inside every single atom. On one side, you've got the pull from the positive nucleus, yanking those electrons in and trying to make the atom smaller. But fighting back is the push. The inner electrons kind of block that pull, and adding more layers, or shells, pushes the atom's edge way farther out.
Okay, keeping that tug of war in mind, let's try a little thought experiment. If you were to trace your finger from left to right across a row on the periodic table, what do you think would happen to the size of the atoms? Would they get bigger, smaller, stay the same? Let's see what the data actually says. And wow, when you actually plot it out, you get this amazing pattern. It's not a straight line at all. Instead, you see this beautiful repeating rhythm of peaks and valleys. It's almost like a chemical heartbeat, just rising and falling with perfect timing. So what are we actually looking at here? Well, those super high peaks, those are always the group 1 elements, the alkali metals. They're like the giants of their row. And the deep valleys down at the bottom, that's the noble gases, way over in group 18. They're the smallest atoms in each row. And just like that, we found our first rule. As you go from left to right, atoms actually get smaller. And this visual shows you exactly why that happens. Look at boron, carbon, and then nitrogen. As you move from one to the next, you're adding more protons to the nucleus. That means the inward pull is getting stronger. But, and this is the key part, the new electrons are all being added to the exact same outer shell. So you've got a stronger magnet pulling on the same layer of electrons. The result? The whole thing just shrinks. Okay, so that's going across. But what about going down a column? Well, here, the trend completely flips. Every single time you move down one step, you're adding a whole new shell of electrons, a completely new energy level. That extra layer is a massive jump in size, making the atom way, way bigger. So let's just nail this down. Atomic size gets smaller as you go across a row because of that stronger nuclear pull, and it gets bigger as you go down a column because you're adding entire new shells. Pretty straightforward, right? Now, let's use this one rule to unlock the others. All right, now that we got a handle on size, let's look at the first big domino to fall because of it, an atom's grip on its own electrons. This is what we call ionization energy, and believe me, it is completely linked to the atom's size. Ionization energy sounds kind of complicated, but it's really just a fancy way of saying the price you have to pay to steal an electron. That's it. If an atom has a super tight grip on its electrons, it's going to have a high ionization energy. It costs a ton of energy to rip one away. But if the grip is loose, the ionization energy is low. Easy peasy. The best way to picture this is to think of the nucleus as a powerful magnet, right? So if an electron is hovering really close to that magnet, it's going to be a real struggle to pull it away. But if that electron is way out on the edge, far from the magnet, and maybe has some other electrons in the way, well, it's much, much easier to just pluck it off. And this sets up a really beautiful, super simple inverse relationship. Small atoms, their electrons are close to the nucleus, so they have a super tight grip, which means high ionization energy. Large atoms, their electrons are far away, so they have a loose grip, which means low ionization energy. See? Size directly tells you about its grip. It's that simple. Okay, we've got size down, we've got its grip on its own electrons.
Now it's time for the final piece of this puzzle. How good is an atom at attracting other electrons when it's trying to make a chemical bond? And this property has a name: electronegativity. Now, the key difference here, and you gotta get this, is we're not talking about stealing an atom's electron anymore. Now we're talking about how strongly it pulls on electrons it's sharing with another atom. Think of it as it's pulling power in a chemical tug of war. And guess what? The trends here follow the exact same logic we've already figured out. As you go across a row, the atoms get smaller and their nuclei get stronger, so they have a much greater power to attract electrons. And as you go down a column, the atoms get bigger and more shielded, so they have a weaker pull. It's no wonder that fluorine, sitting up there in the top right corner, is the king, the most electronegative element there is. So, we've covered size, we've covered grip, and we've covered attraction. Now for the grand finale, the payoff. Let's tie all these ideas together and see what they really tell us about how the world actually works. And boom, here it is, all laid out. Just look at how clean that is. As you go across, the size goes down, but the grip and attraction go up. As you go down, the size goes up, but the grip and attraction go down. These simple, elegant, interconnected patterns, these are the secret rules of the periodic table. Okay, but so what? What does this actually predict? Let's make it real. Take a classic metal like sodium over on the left. It's big, it has a really loose grip on its electrons, and it's not great at pulling on other electrons. So in a chemical reaction, what's its game plan? It's going to lose its electron. It practically gives it away. Now contrast that with chlorine on the right. It's small, has an iron grip, and a powerful attraction. What does it want? It desperately, desperately wants to gain an electron. And that right there is the whole shebang. This is the bottom line. By just understanding these three simple connected trends, we can predict an element's entire chemical personality. We can predict how reactive it'll be, if it's going to form a positive or negative ion, what kinds of bonds it's going to make. I mean, we can predict the fundamental behavior of pretty much all matter. It's incredibly powerful. Which leaves us with one last kind of mind-blowing thought to chew on. How is it possible that these few super simple rules, just about size and attraction, repeating over and over across a little more than 100 elements, can combine to create the absolutely staggering, infinite complexity of our entire universe? Everything from a simple grain of salt to the most distant fiery star. It all just comes back to these hidden patterns on this incredible map.